Big concepts, kind of easy stuff. We've been talking about integration, and that is one of the two big questions in calculus. How do we find the area under a curve? And in this case, we're just saying, from point A to point B, starting point, ending point. How do you get that area? Well, first of all, I want to talk about the area. When we say that area, we always mean from f of x to the x-axis. It stops right there at the x-axis. If you had a graph that was below, well, I'd be talking about the area from that function still to the x-axis. Notice now the area is above the function, but it is the area between the x-axis and that function. Okay, so that's what we mean by the area there. We've also looked at how we can estimate this. We use a whole bunch of rectangles. Could be trapezoids, some basic geometric shape. So we're using, say, rectangles, and I just use the left-hand limit up top here. These are actually named after George Bernhard Riemann, a German mathematician, scientist of great note who laid the foundation for basically the theory of relativity in Einstein. Did some amazing stuff, but he might be best remembered by all the college freshmen who take this for creating what's known as Riemann Sums. Now, I'm not saying he created these, but he was named after him. And so basically, this is just the same explanation. I'm adding up the heights and the widths. Technically, I'm going to skip a bunch of jargon here, but maybe your college professor is into it. The delta x sub I means how wide is each rectangle? Is it the first rectangle, the second, the third, the nth rectangle, or the ith rectangle? I going from 1 to n. So if you have 10 of them there, you might have 1, 2, 3, or 10. That's called the partition, and that just tells you how wide. They don't have to be equally spaced. Sometimes it's advantageous not to have them equally spaced. But of course, if you want to have an accurate area here, we use a limit and let the number of Riemann sums, the number of rectangles, approach infinity. Likewise, they would also say the largest or widest partition would be approaching a width of 0. That is another way to define it. This, of course, is the height. That's just the function. C of I represents any number between the left and right-hand points on a rectangle. So it could be the left side, the right side, anything in the middle. Doesn't matter which one. They're just saying, hey, find a height in there. That's our estimate. Yay, that's what Riemann sums are. So when we talk about estimating it with rectangles or trapezoids, we're talking about a Riemann sum. That's the quick and short way of thinking of it. And we all know the shortcut for finding this in some way, but has it been explained yet? Now we're getting into something called the definite integral. And so if you take a normal integral sign and you put your lower limit, or your starting point on the bottom, and your upper limit, or your ending point on the top, that represents the area under here, not an equation. Literally a number. If your area is 10, you're going to get 10. So it's more than just the normal integrals we've been doing. It is the definite integral. Unlike the indefinite integrals that have the plus c and an entire family of numbers or functions that represent the answer. So I'm going to break down a few basic rules here about definite integrals. So first up isn't even a rule. When you find the area under this, you're going to get a positive area, right? I know that from A to B, I have a positive width, and I know my function is a positive height. When I find the area of something underneath a graph, and I'm finding all these little rectangles here, well, I'm still going from A to B, so I have a width of each rectangle that's positive, but now every height is going below the x-axis. It has a negative height. This would have a negative area or a negative value for that integral. It seems weird, but it is true. We don't have many things in the real world with a negative height, but on a graph, a negative could represent a direction or another thing. Likewise, when we get up here, what if I switch the direction, my starting and ending points? Well, if I start on the right and go left, now I have the same height I did before, but a negative width. In other words, I'm just switching the direction. It's now going to be a negative area. If I start and stop at the same point, the area is